Hello everyone, welcome back to Nated Engineering. Today we are going to look at strain energy. Before we go to what strain energy is, I want us to look at elasticity. By now, we already know that elasticity is the property of a material to return to its original size when the load causing the deformation is removed. When we apply a force to a body, the body will change in length, either decrease in length or increase in length, depending on the force that is applied on that body. If the body is elastic and we are still within its elastic limit, it will go back to its original size when the force is removed. That is what elasticity means. What causes the body to go back to its original size after the force that is causing the deformation is removed is what we call strain energy. Strain energy is the energy stored in any object which is loaded within its elastic limit. So we are having a body and we apply a force of F. This is compressive force. It's a compressive force, meaning this force will shorten this object. We will end up with something like this, with this being our change in length, this being our original length, and this from here to here being our final length. This material, we assume that it's elastic and we are still within its elastic limit. The force is now removed. The strain that developed inside this object, the strain energy, as the force was being applied, will now push the object back to its original shape. And that is what we'll be dealing with, which is the strain energy. Strain energy is equals to work done. We know work done, it's given by the force times the distance moved. This will be equals to our strain, which is represented by the letter U, which will be U. But now, instead of us using the force, the final force or the maximum force, here we are going to use the average force. Why? To explain that, we are going to look at the example of a spring. We are having a spring and we are trying to compress this spring. As we are starting, the force that we are applying to the spring is 0 currently, 0 Newton. This will be the force at the beginning. We keep applying force. We can all agree that the shorter the spring gets, the more force we will have to apply for us to be able to achieve a shorter distance than what we will be having currently. So the force, as the length of the spring is decreasing, the force that we are applying to the spring will have to increase. Let's say we end up to, let's say here kilonewtons, we end up to a force of maybe 50 newtons. 50 is supposed to be kilonewtons, not the other way around. Kilonewtons. So here we cannot use this force because this is not what we initially started with. So here, where we are supposed to put the force, we are going to put what we call an average force. So F will be equals to, in the case of the example that I've just erased will be equals to 0 plus the 50 kilonewtons that we had at the end divided by 2. So our formula will look like this: 0 plus F divided by 2, which will be equals to half F. And then we look at the distance. The distance moved will be equals to what? The distance moved will be equals to, let me erase this. The distance moved will be equals to the change in length. Therefore, the formula to calculate strain, it's given by U, it's equals to half force, which is the average force that we're having here, and then times X. This is our formula to calculate for strain. If we were to have a graph representation of what we have here, it will look something like this. This will be our strain, or we can just say X, which will be, yeah, it's strain, never mind this. And this will be our force applied. So as the force is increasing, the strain will also increase, and then it will be something like this, where this shape, this part, this portion right here, will represent the work done. This area is representing the work done, and we know this. We can see that this is a triangle. How do we calculate for the area of a triangle? We say half of the height times the breadth. Yes, I wrote it the other way around, which is equivalent to what we had for strain, which will be force times X. In this case, it will be height times breadth. The height will be the force, and the breadth will be the change in length, which is X. Yeah, I was correct here, which is X. Remember, we are having this diagram. So now from the diagram, we're going to add our strain. So we're going to add strain 1 here, which is U1. We're going to add strain 2 here, which is U2, and U3. And our total strain will be given by strain number 1 plus strain number 2 plus strain energy number 3. Take note that this it's strain and this it's strain energy. They are not the same. And then we will be having a new component on our diagram, which is our strain energy. Then we have 3 ways in which a force can be applied to a body. It can either be applied suddenly. We have what we call suddenly applied load. And then we have what we call gradually applied load. Then we have the last one, which is shock load. On our next lessons, we are going to cover these 3. But for this lesson, I will leave it here, and I will see you on the next lesson.